जय देवी जय श्री सरस्वती ಎನ್ನರುನ್ಮಾಂದಿರದೆ ಇರು ನಿತ್ಯ ಸುಮತಿ ಜಯ ದೇವಿ ಜಯ ಶ್ರೀ ಸರಸ್ವತಿ ಧವಳ ವಸ್ತ್ರ ಧವಳ ನಗೆಯುಳ್ಳ ತಾಯೇ ಧವಳ ವಸ್ತ್ರ ಧವಳ ನಗೆಯುಳ್ಳ ತಾಯೇ ಜ್ಞಾನದ ಬೆಳಕನ್ನು ಆರದೊಲು ತಾಯೇ ಜ್ಞಾನದ ಬೆಳಕನ್ನು ಆರದೊಲು ತಾಯೇ ಆರತಿಯ ಮಂಗಳದ ದೇವಿಗೆ ಉರಿಸೋತ ಆರತಿಯ ಮಂಗಳದ ದೇವಿಗೆ ಉರಿಸೋತ ಹಾಡುವೇನು ಸತತ ಒಲಿಯಮ್ಮ ನಿರತ ಹಾಡುವೇನು ಸತತ ಒಲಿಯಮ್ಮ ನಿರತ ಜಯ ದೇವಿ ಜಯ ಶ್ರೀ ಸರಸ್ವತಿ ಎನ್ನಲಿ ನೀನಿಹೆಯೋ ನಿನ್ನಲಿ ನಾನು ಎನ್ನಲಿ ನೀನಿಹೆಯೋ ನಿನ್ನಲಿ ನಾನು ನಿನ್ನ ಮೋಹ ಜಾಲ ಎಂಥದೋ ಏನೋ ನಿನ್ನ ಮೋಹ ಜಾಲ ಎಂಥದೋ ಏನೋ ಸೃಷ್ಟಿಕರ್ತನ ರಸಿ ಪಣಿವೇಣಿ ವಾಣಿ ಸೃಷ್ಟಿಕರ್ತನ ರಸಿ ಪಣಿವೇಣಿ ವಾಣಿ ಎನ್ನ ಕೈ ಬಿಡದಿರು ಗತಿ ನೀನೆ ಕಲ್ಯಾಣಿ ಎನ್ನ ಕೈ ಬಿಡದಿರು ಎನ್ನ ಕೈ ಬಿಡದಿರು ಗತಿ ನೀನೆ ಕಲ್ಯಾಣಿ ಜಯ ದೇವಿ ಜಯ ಶ್ರೀ ಸರಸ್ವತಿ ಎನ್ನರೋನ್ಮಾಂದಿರದೆ ಇರು ನಿತ್ಯ ಸುಮತಿ ಜಯ ದೇವಿ ಜಯ ಶ್ರೀ ಸರಸ್ವತಿ.
Thank you, Ms. Chandana, for your soulful rendition. Now, to extend a warm welcome to all our esteemed guests and provide an overview of the program, I now invite Dr. U.B. Madheswamy, Professor and Head and Coordinator of this program, Department of ECE.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. A very great morning to all of you. It gives me immense pleasure to deliver the welcome address in this august gathering. At the outset, I submit my humble pranams at the lotus feet of Sri Sutturu Guru Parampara and seek their divine blessings. It is my honor to welcome Dr. Naukant Bhatt, Dean Interdisciplinary Science, Professor, Center for Nanoscience and Engineering, Indian Institute of Science, Bangalore, our proud alumni, the chief guest of today's function. You will also be delivering a keynote address on From Vacuum Tubes to Silicon Revolution. I request Professor Tyagaraja Murthy to hand over the gift of life as a token of our gratitude to Dr. Naukant Bhatt. It's a distinct honor to welcome our esteemed guest, Dr. B. Suresh sir, Director, Technical Education Division, JSS Mahavidyapita, Pro-Chancellor, JSS AHER and JSS University, Noida. as the visionary behind this professional development program. His leadership and guidance have been instrumental in its creation and success. We are deeply grateful for his presence here today. Now I request Dr. Sudarshan Patel Kulkarni to hand over the tree lead to Dr. B. Suresh sir as a mark of our respect. We are truly honored to have with us today our Honorable Vice Chancellor Dr. N. Santosh Kumar, another guest of honor at this inaugural ceremony. His unwavering support and guidance are a perpetual source of inspiration, motivating us to deliver programs like this. I request Dr. M. G. Veena to hand over the young plant to Dr. N. Santosh Kumar as a token of our respect. I take this opportunity to welcome our respected Registrar, Dr. S. A. Dhanraj, to this inaugural ceremony. His invaluable assistance with all official formalities greatly accelerated the smooth realization of this program. Now I request Dr. Rita S. Prasad to hand over the saplings to our Registrar as a token of our gratitude. Now I welcome our beloved Principal Dr. C. Nataraju, who always inspires us to organize these kinds of programs very often. Now I request Dr. Gayatri HM to hand over the gift to our Principal as a token of our gratitude. I welcome all deans, associate deans, university officials, HODs, faculty from other departments to this inaugural ceremony. I also welcome the press and media people who are present here to give a wide coverage to this program. I request Dr. Anupama S. and Dr. Pavitra DR to hand over the flowers as a token of our gratitude. As we draw to a close, I welcome the participants from JSS-AT Noida, both Engineering College and University, JSS-AT Bangalore, JSS Polytechnics, JSS STU, research scholars, PG scholars to this inaugural ceremony of 3-day professional development program. So now I would like to give a brief note about this workshop. The field of semiconductor technology is constantly evolving with new materials, designs and manufacturing processes being developed all the time. So continuous learning is crucial to stay relevant. Semiconductors are everywhere, from smartphones and computers to cars and medical devices. Semiconductors are the backbone of modern technology. Understanding them is essential for everyone in a technical field. Recognizing the growing importance of semiconductor technology, our visionary director has conceptualized the idea of this professional development program and brought together the concerned faculty from all technical institutes of JSS Mahavidyapita under one roof for the comprehensive update on the latest advancements. Thank you, sir. The objectives of this professional development program are to educate and emphasize the significance of semiconductor technology within the academic setting, to analyze and explore the current state and potential advancements in the field of semiconductor technology on a global scale, to support and enable the opportunities for the creation of a center of excellence in semiconductor technology. The resource persons for this PDP are academicians from premier technical institutes, consultants, and top-level technical people from industries who are pioneers in the field of semiconductor technology. As per the advice from our director, we have prepared a workbook comprising of the running text related to each session, followed by a set of questionnaires provided by the resource persons. It's a mandate for all the participants to complete the workbook activity before receiving the certificates. Dear participants, our management has magnanimously funded a considerable amount to facilitate the updation of our knowledge in this emerging field. I request everyone to participate with keen interest and enthusiasm and reap the most benefit out of this professional development program. Thank you, one and all.
Thank you, sir, for your earnest welcome. I now request Dr. Rudraswamy SB to formally welcome Dr. UB Madeswamy, sir, to this event. Thank you, sir. No event is truly auspicious without the ceremonial lighting of the lamp, the symbol of knowledge and enlightenment. I now request all our esteemed dignitaries to kindly come forward for the lighting of the traditional lamp and symbolically inaugurate this program, and also for the prudent tribute to Swamiji. May this light guide us towards the wisdom and progress. Thank you all dignitaries. The culmination of this efforts is reflected and carefully curated in a form of a workbook designed to enhance the learning experience of this program. I now request all dignitaries to join in the official release of the workbook. Thank you, esteemed dignitaries, for this momentous release. Now, it's my honor to invite Dr. A.N. Santosh Kumar, Vice Chancellor JSSSTU, to deliver the opening remarks.
Ellarigu namaskara. A very good morning to everyone. At the outset, I submit my most respectful pranams to the lotus feet of His Holiness, Sri Guru Shri Shivaratri Jeshikendra Mahaswamiji, and seek the divine blessings. Our respected Chief Guest, Dr. Naukant Bhatt, Director, Technical Education Division, Professor B. Suresh, Registrar Dhanraj, Principal Nataraju, Head of the Department, P.B. Madhav Swami, all the other coordinators of this 3-day professional development program on scaling the future, trends and challenges in semiconductor technology. My colleagues from the university and the college, all the participants from JSS Science and Technology University, JSSAT Bangalore, as well as JSSST Bangalore, Noida, and JSS University, a newly formed university, Noida. All others who are present here, especially the friends from press and media. It's a great pleasure to be a part of this inauguration, a 3-day professional development program. Our chief guest, Dr. Naukant Bhatt, is a truly distinguished alumnus of this institution. In spite of his extremely busy schedule, he agreed, was so kind to agree and come here to inaugurate this particular professional development program and also deliver the keynote address. He's always been supportive of all our activities at the university and the college. Thank you, sir. This entire program was conceptualized by our director, Professor B. Suresh. We have been conducting these kind of workshops from a very long time. Number of workshops we are conducting, conferences we are conducting. But he said, there should be a platform where our own people should come. They should all get together and we should invite some of the best in a particular field and see that the knowledge is updated. They learn the new things and they get a totally different perspective altogether. Last week, some of you were here, also attended the research conference which we organized. So first up, today we are having this. I think in the series, we are also having a workshop on AI and emerging technologies with AI. And coming, also we have a program, 3-day program on modern management practices. So this is going to become a feature, in the coming days and years. The objective of this particular program, I think Dr. Madhav Swami started that. First of all, we should all understand what is the potential and importance of the semiconductor technology. Today we're talking of semiconductor technology. Is one of the most dynamic and transformative fields which is shaping our world and shaping our lives. So how many of us really know what is driving this particular semiconductor technology? What is the potential of the semiconductor technology? What all it can do? Why this kind of importance is being given today? So with that objective, we set out this particular workshop. And very rightly said, from your laptops, smartphones, including the artificial intelligence systems that we have today, 5G, all the environmental issues we are having, equipments, systems, all of them are basically driven by semiconductor technology. They power our digital economy. So today, country is talking of digital economy. If you want to really drive digital economy, then without semiconductor technology, it is not possible. And through this, we can also solve some of the humanity's greatest challenges, from healthcare to climate change. That means it's quite literally the brain behind the digital revolution what we are having in this particular country. The second important objective with which we started this workshop is to address and understand what are the current trends. Right? So I was just going through some literature on semiconductor technology. Right? They are now talking in terms of newer fabrication techniques, newer design methodologies, and with the advance what we have in the field of nanotechnology, nanoscience, nanomaterials. I think he's an expert on that. He will definitely address these issues. The limit of technological version is now increasing. So you have to understand what we are currently seeing in terms of semiconductor technology itself. So remarkable advancements in the areas like node processes, new materials and novel chip architecture are also the top of the town today when you talk of the semiconductor technology. Then what are the challenges? We read only some books here and there and some journal articles and see what are the challenges. But all the persons who come here with academic and industry background, they're going to talk and take us through the various challenges what semiconductor technology, the industry itself is facing today. One of this one I found out is the geopolitical tensions. Talking in the morning, we're having breakfast also. The kind of sanctions and the tariff wars that we are seeing today. All these are challenges that we have to overcome. Similarly, supply chain disruptions, like some of the ports across the globe, they're all completely, you don't have space to even transport material from one country to another country. So these are challenges, how to overcome these. Major concern today throughout the world is sustainability concerns, right? With use of all these technologies that is coming day in and day out, some of them even recklessly, you see technologies. How do you address these sustainability issues? There are very many challenges. All these we are going to discuss and deliberate over the next 3 days. The other objective is to bring together all the faculty members from the 3 institutions, the researchers, the educators, the practitioners from the academic institutions and also industry to deliberate on these pressing issues and challenges. The government of India and as well as the government of Karnataka here, they have come out with various schemes to promote, support the semiconductor technology itself. There is a Semicon India program where there is a funding of 76,000 crores by the government of India. There is also a semiconductor mission, right? The India Semiconductor Mission, which is financing these startups with new ideas in chip design, novel ideas in semiconductor technology. Everything the government cannot do. So therefore, academic institutions like ours, we should also chip in and say we can also contribute. We have our own step, Science and Technology Entrepreneurs Park. So we can take some of the ideas coming out of this, work towards a product and then take it to the step and try to also have a startup and including encouraging entrepreneurship. In fact, 50% of the project cost in some cases are funded by the government, which is not seen everywhere, right? So that means that is the kind of importance what this semiconductor technology today is garnering. And the most important is to have a collaboration. We have always been trying to have collaboration, with various academic institutions and industries. Today, a lot of people are going to come, right? Today, tomorrow, right? The next 3 days. So we are going to have people coming and talking, and we can definitely collaborate some of them and see how this semiconductor technology can be and the design, etc., can be taken forward. So at the university also we are trying to establish an ecosystem of research, innovation and collaboration. In this regard, as the head of the department was saying, we have already thought of setting up a center of excellence here in semiconductor technology, and the ideas from here can all be used to set up this particular COE so that we can train our faculty, train our students. And in the same regard, we also are starting from the coming academic year, a MSc program in semiconductor technology. That's the first of its kind, in this particular region, where a master's degree program is completely dedicated to the semiconductor technology itself. We want to prepare our students for the future of the semiconductor technology. Also, the active research on nanotechnology, nanoscience and nanomaterials being done at the Department of Chemistry, Polymer Science, and a lot of others are trying their hand on all this. But it requires a little bit of focus and probably direction. These 3 days definitely is going to help you in going in the right direction. The Department of Electronics Communication, led by Dr. U.B. Madheswamy, has taken extremely full and putting a lot of efforts in bringing the right people to this particular 3-day professional development program. And I request all the participants to actively participate. The concept of the workbook is simply not just for this one here. Each one of you at the end of the day should give there will be, I think, question and answers also. You should attentively of all these. At the end of the day, we'll also assess how much we have all learned together in this. So I wish this particular program for the success and hope this is going to be extremely fruitful for all the faculty from Mysore, Bangalore, as well as from Noida. Thank you.
Thank you, sir, for your inspiring words and insights about the trends and challenges in the semiconductor technology and also highlighting about the sustainable concerns. Thank you, sir. I take this opportunity to welcome Dr. Prasenjit Singh, the Associate Professor at IISc, who has assembled. It is now my pleasure to invite our guest of honor for today's program, Dr. B. Suresh sir, Director, Technical Education, JSS Mahavidyapita, to address the gathering.
Good morning, everyone. At the outset, I convey the blessings and greetings of His Holiness Swamiji for this success of this professional development program. As mentioned by Dr. Madheswamy and Vice Chancellor, this program is basically for enriching our faculty to understand the growth and progress that is happening in the specified fields of the field. So that's why we're having this program. And for this program, we have our honored chief guest, Dr. Naukan Bhatt. Sir, it's a pleasure to have you here, and the few minutes we spoke was very exciting for me. Our Vice Chancellor, Registrar, Principal, and other dignitaries who have come here to speak, faculty, colleagues, and students and scholars who are gathered here. At the outset, I would like to congratulate Dr. Madheswamy and his team for putting this program together. I think it's very important that once we convey some ideas, somebody to carry it forward. And Dr. Madheswamy diligently carried out that responsibility, came frequently, discussed, and wanted to see that whatever he does makes an impactful thing. So I congratulate you and the team for putting this team together. And perhaps you are the first in the series in the JC and STU ecosystem to put this type of faculty development program. Research conference was different, but in the FDPs you are the first to start. I think I congratulate you for that. I am a pharmacist, as you all know, so I do not know much about your technology. So when we talk about conductor as a schoolboy, I used to think only about the conductor in the bus, who is there uh, trying to sell tickets and push across a little bit the crowd and do it. Then when I went to a little higher classes, like go to ninth, 10th, where they started talking about good conductor and bad conductors. So then I understood a little bit, oh, there is a meaning beyond the conductor who's giving tickets. But I think the good conductor or bad conductor was doing the same job like a conductor. That is, the good conductor allowed all the electrons and others to move around and be able to efficiently carry out their process of taking forward what they wanted to do. And the bad conductor just sat in one place and didn't want to allow anyone to do and just check the tickets and send them in. Then it's up to them to see what they wanted to do. So then I was thinking, okay, that's a very nice equation of science and real life example. That's what was there. Then I forgot about the good conductor and bad conductor because it did not come into my studies further in pharma. Of course, while using heat, we knew I should not touch this while electricity is there. We know that part of the good conductor, bad conductor, and went on to pursue my thing and then got into administration. But when I landed up trying to understand technical education, then I came across the semiconductor. Now, what is the semiconductor? Then I became very inquisitive and tried to update my knowledge on it. Then I brought my own equation. This semiconductor is the one who rises to the occasion whenever required and moves forward to carry out the roles. He doesn't have to do all the time running around selling tickets. You can buy the ticket and sit in the bus, but when there is a situation, this conductor moves around. When a stimulus is given, the electrons move around and try to carry out their roles which they are doing. So this was my simple understanding I made myself about the semiconductor. Now, looking at this, I was speaking to one of the industry experts about the advances that are happening in technology and how we at JSS are very aggressive in changing the syllabus and doing things as per the current trends. Then he asked me one very simple question. How frequently do you update your syllabus? I said, sir, once in 4 years because the first batch has to go out and then we again change the syllabus which you are doing. He looked like he had a short circuit because he said the technology is advancing so much. So if you want to talk about 4 years, so by the time the student is passing out, he is obsolete. So he said even the Moore's law talks about doubling of the transistors on the chip every year and reducing in the cost. So you are much more slower than the Moore's law. And now even Moore's law is failing because of the quantum computing that has come in and the place and position where it is occupied. Interestingly, again today's newspaper I saw Lam Research has come forward to invest about 10,000 crores in India in setting up the semiconductor industry. So if these type of investments are coming to India for developing a particular type of facility or capability in our country, you can imagine what the focus of our country is and what type of graduates are expected to go and carry out these responsibilities. So if you are going to give an obsolete student to the field and and then you expect him that he should go and find a role and play which is there. At least the thinking process should be there. Your curriculum may be not be able to move as fast as the technology, but at least the thinking capability of the student should be able to move where he can source this information, advance this information to his mind and be able to do it. So you have to have a conducive environment and that's what I keep telling whenever now I have got a new phrase word to all my teachers who come to me, whether it's VC or registrar and all. I started telling them now stop being CPUs and become GPUs. Do the parallel processing. Don't try to wait to go in a single sequence to achieve the objectives. Of course, they are little annoyed with me, but I can't help. I am a type of person who would like to push and see things happen, and not for my personal gain, but for the good of everyone. Now, again, one of the important things which I am trying to tell, why the leadership of our country is also so conscious. Our Honorable Prime Minister in the AI Summit, he has told some flaws in the AI capability also. He has said that if you ask a command to AI to draw or give an image of a person who is having a left-handed nature and writing, the AI is not able to give, and it gives the image only of the person who is having the right-handed capability to do it. The reason is because the data that has gone into AI is always relating to the right-handed person and not the left-handed person. So it is not able to give it. And in fact, people did try and found out whenever they gave the command to the or a prompt to the thing, and it gave the left-handed image. And similarly, there are in the AI other biases also. Like if you look at dark persons to be given, it doesn't consider them as the human form still. And there are other such flaws in the AI system, which only humans, as we can explore, can be able to achieve these objectives. And another interesting fact which I'm trying to tell all this is to sensitize how fast this technology is advancing and how fast people are embracing it also and moving forward, and they have similar expectations from us. Today again I saw a very interesting article and video related to that about University of Oxford now for successfully breaking the teleportation process to happen. They have successfully, between two quantum computers, they have been able to shift the information and try to link together. And if a change is happening in one computer, it happens in the other. By teleportation process, it's able to achieve that. Now, this type of technological advancement, how does it make? Today, as you know, for if you, one of the major impact it will have on the internet communication which we are having. Now, through quantum computing and through this teleportation, what is possible is the encryptation becomes obsolete now for you. No need for encryptation for you. You are able to do it without encryptation and be able to carry out the things, whether it's in the healthcare or whether it is in financial or other services, defense, the government data, all these things can be will be able to be achieved in a better performance. This is the information that I could gather from the advancement which University of Oxford is able to do. So it is going to be a game changer by in its own way. So are we going to read about this teleportation 10 years, 15 years from now, or we are going to talk about this as a relevant topic of research and advancement in our curriculum to the students? Can there be in a curriculum a flexibility of teaching the students some of the advances that are happening, which a teacher can choose of choice and tell them that, okay, this is my lesson and this is what I'm going to teach you in the current trend. And maybe that chapter becomes a part of your learning and question and evaluation, everything. See, typically what we do, if a student who has studied in got enrolled in a particular batch, till he passes out, that same question paper and same syllabus is used for him to teach. Because we feel, no, he will object, he will go to court. But will the technology remain there only for him? Whether this will go out with the person who is studied, joined in 20, say, in somewhere in 2010, and he is passing out in 2024, and you are going to give him the same 2010 till he passes out. Will the technology remain same for him? No. So I think we have to again make it clear even in our regulations that if you fail, you will be adopted only into the next regulation which is there, and you have to adapt and move forward with the system. I think these are the teaching initiatives which we should take up to make sure that which we are able to do it. Now, I had a wonderful idea when I was thinking, like, okay, is it possible to find out whether I can use a GPU inside me and try to enhance my capacity and see how I can do more work because I'm burdened with so many things. I was thinking like that. Well, that's not an impossibility. Already the Elon Musk labs are working on neural links, and a link between the humans and the chips is not far away. And these type of neural networking is going to, neural links are going to make a difference to the science. Now, this is so exciting, all this growth and development that is happening around me. I am just feeling helpless that I wish I was younger and like a student like you, so I can be in this environment to learn more and more and be a part of this excitement that is happening. So I think I have shared my thoughts, my feelings, my emotions to all of you about it. And I want all our faculty to understand this and try to see how we can bring about this type of environment and ecosystem in that, where continuous learning is there in our institution, but parallel learning also takes place, that we are able to give opportunities to students to choose, speak, and try to learn what is happening. And they are, when they go out, they go with the same excitement and enthusiasm to go into the industry and prove themselves. I think this is something which what I would like to leave as a message here. Once again, I congratulate the Vice Chancellor, Registrar, Principal, and all of the other leaders here who are taking this initiative so passionately to see how do we make JSS Science and Technology University and SGEC to the next level. We are known for our reputation, for our education, quality of education, the placements and all that. Now, can we go beyond this is the question which we are asking. And that's where all these initiatives are leading. So I'm sure this will go very well. And I wish this FDP all the very best. I'll try to be here and learn more and try to see whether I can still become advanced in my knowledge in this field. Thank you very much.
Thank you, sir, for your invaluable insights about the technological advancements and also gave us an eye-opening towards our preparedness for the same. Let's try to align ourselves for this excited journey in the technological advancement. To introduce the esteemed chief guest of today's function, I now invite Dr. S.B. Rudaswamy, coordinator of this program.
Good morning, everyone. Firstly, I offer my humble pranams to the Suturu Guru Parampara and seek his divine blessings of His Holiness Swamiji. So it's my pleasure and privilege to introduce today's chief guest, who also my mentor to this august gathering. Professor Navkambhat obtained his Bachelor of Engineering in Electronics and Communication from our own SJC in the year 1989 with a gold medal. So it's a privilege to have you, sir. Later he joined Indian Institute of Technology, Bombay for his Master of Engineering program in Microelectronics, and he completed in 1992. Later he received his PhD in Electrical Engineering from Stanford University in 1996. Before joining Indian Institute of Science, he worked at APRDL, Motorola in Austin, Texas until 1999 on advanced CMOS technology development. He is currently the professor in the Center for Nanoscience and Engineering and also the Dean Interdisciplinary Science at the Indian Institute of Science, Bangalore. His research is focused on nano-electronic devices, electrochemical biosensors, chemical-resistive gas sensor, and also on the membristors. So he is accomplished with a lot of awards and the things. To name a few, he is a recipient of several awards, including the IBM Faculty Award, Dr. Abdul Kalam Technology Innovation National Fellowship and Outstanding Research Investigator Award from the Government of India. He is also a recipient of the prestigious Infosys Prize in Engineering and Computer Science from the Infosys Academy. He is the Fellow of INAE and Fellow of IEEE. He was the editor of IEEE Transactions on Electronic Devices from 2013 to 2016. He is Electron Device Society Board of Governors member since 2015 and is currently the co-chair, Nanotechnology Technical Committee and Vice President, Educational Activities. He is a distinguished lecturer of IEEE Electron Device Society. He is also the co-founder of the startup Pathshore Healthcare Private Limited, which has commercialized first of its kind lab-on-pump device for point-of-care diagnosis of multiple chronic disease. Sir, we are really happy and we welcome you once again, and we are eager to hear you, sir. Thank you very much.
He's going to be there first.
Sir, small felicitation.
Very good morning to all of you. It's always a pleasure to come back home. As Dr. Rudraswamy was mentioning, I did my Bachelor of Engineering in Electronics and Communication way back between 85 to 89. So since then I have been interacting with JCE on many occasions. Now this is also a very important context, I understand, is that all the faculty from different JSS institutions have come together here, which is a very unique program that you have initiated. We are sort of at crossroads today in the context of education and research, right? Especially in the academia, because the way the developments are happening in large language models and AI, be it ChatGPT or many other versions, right? So we are now asking the question, how should we be engaging with the students in the coming years, right? So that is a very, very challenging task. I think it has become even more important today to ensure that we engage with students in many creative ways, right? We always have to reinvent ourselves. I think perhaps such events, the 3-day events that you have here, give opportunity for all of us to reinvent ourselves. You could also learn from your peers, right? So I think I'm sure that you will make the best use of this occasion. So today my talk is on a related subject. I've titled it as neuromorphic computing for artificial intelligence, and the director, Dr. Suresh, just mentioned, or maybe it was the vice chancellor who mentioned that about AI conference that happened, and our prime minister's remarks, right? Everybody is talking about AI, but there's also a flip side of AI, and that is what we will talk about today. And that is where the faculty who have gathered here from electronics engineering department, I think they may have a role to play. Really sort of reinventing, rebooting the hardware for AI world, right? We cannot really continue to build the hardware as usual, because that's not scalable. The Moore's law is already hitting its limits, right? So that is where we can again perhaps get inspiration from nature, right? There's a lot of talk happening about neuromorphic computing, and at our center in IISc, my colleague Shritosh Goswami has been leading this effort, and I'm going to tell you a little bit about that in the overall perspective of how we have come a long way in electronics. And I think it's okay, I'm audible, right? So I think this will unnecessarily be an obstruction. Yeah, I think it's okay. Can you hear me at the back? Okay, you cannot really. Oh, okay, that's surprising. Okay. Okay, fine. Is it okay now? Okay, fine. Let me. So this is the outline of my talk. I'll briefly touch upon, how we have come a long way. and why we have this crisis that we are looking at right now. And that sort of leads us to the next topic, which is brain-inspired computing, right? So we have been building chips. These chips have essentially two building blocks, transistors. These are the building blocks for any electronic IC. We have billions of transistors today in an integrated circuit chips, right? And they all have to be interconnected, right? The kind of interconnection that you have will really give the particular functionality for the integrated circuit chip, right? So, these interconnects essentially define what is the functionality of the chip, right? Is there a marker that I can use, or I think there is this problem with, yeah, maybe I'll use the laser marker here. This is better, but that's going on and off for some reason. Yeah, fine. So there was a mention to Moore's law. Gordon Moore, who was the founder of Intel, made this observation in 1965. First integrated circuit was invented in 1958. 58 to 65, he just made an observation in any given year, which is on x-axis, how many transistors were put on an integrated circuit. And he noticed that it was doubling every year, right? And on a semi-log graph sheet, which is y-axis is in log scale, it would plot as a linear graph, right? Which indicates that, it is continuing to happen. It has happened over many, many decades, right? Although it is slowing down a little bit today, we are still trying to sort of progress it, miniaturize, and put as many transistors as possible. The fundamental assumption there is that you are able to miniaturize the transistor, make the transistor as small as possible. This is your building block transistor, which used to be in a micron scale, and today that's in the nanometer scale. It's about 20 nanometer, although the technology is labeled as 3 nanometer, 5 nanometer, the transistor dimension is little more than that, okay? So we have been building these chips since 1958. At that time it was done using bipolar junction transistors. But in late 60s is when we introduced the PMOS technology, P-channel MOS technology. That is when we also had the first computer on a chip, or a CPU, which was again mentioned earlier, central processing unit. That was Intel 4004. And then in 74, we moved to NMOS, where N-channel transistors, which are more efficient compared to P-channel, they became a building block. And we started building more complex chips. And in mid-80s, we actually moved to CMOS technology, where we use both N and P type transistors. And that is what we are using even today. Except that, today's chips are very complex. I will show you some pictures. Today we use what are called FinFETs. These are 3D transistors, not the conventional 2D transistors. And, we are continuing to go in this path. So starting from, as I said, from vacuum tubes to semiconductors, integrated circuit, to the first Intel chip. Just make a note of this. The first Intel chip had only about 2000 transistors. 10 microns was the dimension. And the size of the chip was about 12 mm square, and power dissipation was 1 watt. Right? And today we are building chips with billions of transistors. This is, for example, a chip which was introduced by Intel in 2013, which has many cores. We today talk about number of cores in a CPU. And we are also talking about what are called SoC, systems on chip. This chip, for example, has many CPU cores. It also has what are called programmable elements, which you can do programming in the field, which is essentially a field programmable array. It also has high bandwidth memory. It has a lot of ADCs, D2A converters, which is analog. It also has a lot of RF components. I mean, many diverse building blocks are now getting integrated on a chip, right? That is why we call it SoC. And these are now routinely being built on 7 nanometer, 5 nanometer kind of technologies, right? That is the kind of progress that we have been able to achieve, right? So then, in a nutshell, over the years, we have taken a micro electronics technology to a nano electronics technology, more than 1,000 times miniaturization. And also we have gone from small scale integration, which is about couple of thousand transistors, to a very large scale or gigascale integration where we have tens of billions of transistors on a chip. Right? And this is what is today powering all our IT infrastructure, right? Which we take it for granted. But there is a major issue that is unfolding. It has been unfolding for a few years, but it's really becoming a very serious issue today. While we were scaling the technology over the years, remember this, we had that x-axis in the Moore's law, doubling transistors every year. What we had not shown there was what was happening to the power dissipation in a chip. The power dissipation in a chip is rising exponentially, right? It's actually hundreds of watts of power consumed in a very small chip, right? Often it's said, you know, it's through accurate modeling that the power density in a chip today is more than the power density in sun, right? In a power per unit area. That is how much power we are dissipating on this small silicon piece that we have. Now this is a real problem. You know, why is it a real problem? We will come to that in a minute. This will be a showstopper in terms of how far we can go in terms of scale. Okay, so this is where we really need some new architectures, the new way of building chips, new way of cooling chips. You know, I'm sure Professor Prasenjit, who is here, is an expert in microfluidics and all that. So there's a thought that we can integrate microfluidic channels along with the chips. It's already happening. So we really need solutions coming from different technology worlds, you know, to solve this problem. Now this problem has become even more serious because of the explosion that we see in AI, right? Because AI, what you see is of course software at the front end, software like ChatGPT or any other large language model, which is of course influencing almost every sector of our society. But at the back, you know, what you see in the front is software. You know, at the back, it's all hardware, right? You know, hardware is the chips. If you ask the question, do we have the right hardware to run this AI software? The answer is clearly no. Okay, we do not have that, right? I'll just give you some numbers here to illustrate the point that the AI hardware is extremely inefficient. We have already told you many billion transistors on a chip, and we use many such chips, right? NVIDIA's recent, GPU, if you look at the number of transistors that have, it crosses 100 billion transistors, right? You know, that is how complex this integration is, right? In a data center which uses all these chips, if you see the power dissipation, it's trillions of watts that are consumed in data centers. And that's why today companies like Google, are trying to build this data center firstly in cold, regions, so that your cooling budget is not as much. And also on top of it, you set up a power plant right next to it. Otherwise, through grid power, it becomes very difficult to what is called system in package. I'm sure Professor Prasenjit will talk about that. So this is what is done today. It is not analog. It is not in-memory computing. These AI chips are doing near memory computing, which is all digital. So what we want to do is really analog in-memory computing, and that is where there is this new device which is called memristor. It's a two-terminal device. There is a top electrode and a bottom electrode, and there is a very unique material in between. There are different ways of implementing these memristors. One way of implementing this memristor using what is called a molecular material. Okay, and this is what was invented by Shritosh during his PhD days, and we are building on top of this platform today. So what it does is, if you look at this material, if you look at the IV characteristic of this material, it has a very interesting IV characteristic. Typically, you have a resistor, you do a current voltage measurement, the current increases when you increase the voltage, and current comes back in the same straight line, right? But here, when you are going up, the current is here, and suddenly the current goes up. This is like a switching event. And then there is a hysteresis, right? And then the current comes back down at some other voltage. There are two important things here. There is a hysteresis, there is a switching. Hysteresis indicates of memory, right? You can remember what has happened before. That is what we mean by hysteresis. Switching is, you can do computation using switching. So you see, the same element can do both. It can switch, and it has hysteresis, and hence it can store the information, right? And it can store the information without any degradation. What is shown here is that when you have flash memory in your USB drive, the question is how many times you can rewrite that memory. Today's flash memories, you can rewrite about million times. It turns out this molecular building block, which I said has memory and it can do computation at the same location, its memory is very robust. Its memory can stay as is. This is a low level and this is a high level. Memory always has two levels, 0 and 1. It can withstand that state even after programming for a trillion cycles, right? It can beat the flash memory that we have today. Right? And even in terms of other, metrics of international technology roadmap for semiconductors, be it read current, write erase time, read voltage, write energy, in all these metrics, this can surpass what transistor based circuits can do today. Okay, so now this is a very interesting building block for the following reason. Okay, I think there was one slide. Let me just see here. Okay, looks like that was a comparison between a transistor and a memristor. So transistor is a three-terminal device. We use it as a digital switch, right? It will enable us building processors, building memories, but we are stuck with the digital architecture and at best near memory computing. Memristor now is an analog building block, not digital building block. I'll tell you what I mean by analog building block. It can store and process at the same location, and hence it can potentially enable what is called an in-memory computing. Okay, we will also see what I mean by that. What does neuron do? Right, neuron accepts certain inputs as is shown here, x0 to xn, and it has what are called weights. These are called synaptic weights at the synapse junction, right? Inputs are coming into the neuron. You multiply the input with the weight, and there is something called a thresholding function in the neuron. Then the neuron will fire if your multiply accumulate is more than a threshold, otherwise it will not fire, right? So this is how a neuron will work. Now let's imagine that I have an element, a magical element, which turns out to be the memristor, which can store information. What is shown here, G1 to G2, Gn are conductances. Okay, conductance is a reciprocal of resistance, as you know, and it can store information in multiple levels. if you have from 0 to 1, it can store 0 and 0.1, 0.2, then you have 10 levels. If I can go to 0.01, it can reliably store that, then you have 1000 levels, right? As we will see, this can store more than 16,000 levels, right? So which means my bit precision for storage is not 2 bit, it is multiple bit. It's as precise as it can get. This is 14-bit precision in this particular case. Now, if you apply voltage, what happens is that the voltage multiplies with the conductance, because voltage is coming across this conductance. That is a multiplication step, because voltage into conductance gives you current, right? And along this line, if you have many of these devices, you can add all these currents, and that is addition. So what you are doing along this, two important basic laws that we have studied. Ohm's law enables multiplication, except it is not digital, it's all analog, right? Voltage into conductance gives you current. That's a multiplication process. Along any line that you have, Kirchhoff's law gives a summation of the current. So in one step, I can do multiply and accumulation. And that is what you do in matrix multiplication, right? You take one row, you take one column, each element gets multiplied in a matrix and you add all of them together, right? So if you can actually do what is called a crossbar. Crossbar meaning I have horizontal wires going from left to right. I have vertical wires going from top to bottom. At the intersection of each of these, they are in different planes, by the way, right? At the horizontal wire is running on top, the vertical wire is running at the bottom. At the intersection of each of these, there is a memristor device. Okay, and that is what is called a crossbar. So if you have, in this case, 64 by 64 crossbar, there are 4096 elements, memristor devices, right? So it essentially looks like this. This is the equivalent circuit. You have 64 lines, right, coming from left to right, 64 lines coming from top to the bottom, and at the intersection of each of them, remember what I said, between the two lines there is a memristor. I'm showing that memristor with this equivalent conductance, right? So now you see, what you can imagine is that, let's say I have a vector which has 64 elements and a matrix which is 64 cross 64 matrix. So I can store my matrix 64 cross 64 matrix in this crossbar. Each element of the matrix, which has 64 cross 64 elements, corresponds to each one of these memristors, right? So the information of that matrix element is stored in the conductor, in these memristors. Now you have a vector which is coming in, you apply that vector here, and what you have is a vector matrix multiplication in one step, right? This vector is going across, right? And here you are getting all that multiplication and summation happening instantly. So that is the idea. So this is the crossbar. These are, peripheral electronic circuits. We are still in digital world, right? Although I have built this GPU, not better than GPU, you can call it neural processing unit, but this is also not a right term because already people are using NPUs, right? Apple says that they already have a neural processing unit in their A14 or A15 chip, right? But this is real analog accelerator. So what will happen is that only those jobs which need to be accelerated can be offloaded to this accelerator. So you need D to A converter, you have a crossbar which does the computation, and then it should go back to the compute system. So you have to do a to D conversion. So there's a lot of electronics that you need to build in order to integrate such a crossbar with the rest of the digital system that we have. We cannot replace the digital infrastructure that we have, right? We will augment the digital infrastructure with this neuromorphic engine or accelerators, right? That is the idea. So eventually you may have many RISC cores and many neuromorphic accelerators within the chip, and they are all working together in unison, and that's how your system performance will enhance and your power efficiency will improve dramatically, right? So in this particular case, we were able to show that a matrix multiplication has a complexity of n square, a vector matrix multiplication. There are n square multiplication if you have an n cross n matrix, right? Whereas that order n square can be reduced to order 1, because in a single step you do vector matrix multiplication, right? So we were able to show that this engine that we had built is orders of magnitude better than what NVIDIA can do, right, using the conventional GPUs. Okay. Yeah, I mean, there are details here, but most important detail is that this has a 14-bit resolution, right? These are different conductance levels that is shown here, right? And these two conductance levels are separated by 6 sigma, where sigma corresponds to the noise in the system, and you can easily store data which is more than 16,000 states. That corresponds to 14-bit resolution. There are a few other details which are not very important, but we were able to show that you can actually implement all kinds of matrix multiplication. I mean, your FFT and all the filters that you do, all of that can be done here using this, right? And again, as I said, with substantially better efficiency. And this is just to take home that point that what you have in this hardware here, in the middle, what is shown in yellow is your crossbar. That is the analog processing in-memory computing accelerator. And the rest of the PCB has all that interface circuits, analog to digital, digital to analog, and so on and so forth. As an illustration, what we have done here in this case is taken space telescope data, right, which is a frequency domain data. From that, if you want to do image reconstruction, you essentially have to do a inverse Fourier transform. Inverse Fourier transform has a lot of multiplication and addition steps, and it can be done, of course, with a supercomputer in a digital computing world. It will take 10 power 8 steps. And this is the famous pillar of creation image. This is how it will look, right? The same thing is done using this hardware, not on a sophisticated computer, right? It's done on this. It's done in just 26,000 steps. Just imagine that, as opposed to close to 1 billion steps, which would be required in a conventional digital architecture. You need only about 26,000 steps. And look at the image, right? The image looks almost similar. I mean, this is more than sufficient for your AI jobs, right? Here it is 77.9 dB and here it is 77.6 dB, which is good enough, right? Which is as good as it can get, really. Right? So this is just to illustrate that if you can really build such engines, they can facilitate, the AI jobs and any other signal processing job with phenomenal efficiency. So what we are doing right now is taking this entire PCB that we have, where we had PCB and this crossbar, putting all of that in a single chip, which is what we call a system on a chip. Right? We have all the electronics and also the crossbar on a single chip, right? And the way we are doing it is that we have standard foundries like TSMC. Very soon we will also have a Tata Electronics setting up a foundry in India. So it could be any of these standard foundries. You get the chip made, but these chips do not have crossbars and memristors. Then you bring in this new material on top of this chip, right? This is what is called a heterogeneous integration, and that will enable very, very high performance processing unit for you. Of course, it has many challenges to be overcome. We are working towards that, and we hope that this will eventually lead to a commercial product down the line, maybe 5 years down the line, right? So that is where we are, and it's something very exciting, and we are going through that journey right now. There's a lot of interest in this area, both in academia and as well as startup. right? In the US, in China, in Europe, everywhere. This AI summit that happened in France, as you know, very recently. And even in IISc, we have major initiative in this direction. Right? And this being a semiconductor technology, 3-day symposium, it's important to realize that the semiconductor ecosystem has many things. At the heart, of course, is materials and chips. And then you build these systems and softwares, be it your laptops, cell phones, and all that. But if you don't have this, none of this can come, right? So the total market of this pie that you have is more than $3 trillion as it is today. It's as big as Indian economy, the GDP, right? And the chips and all of that, they contribute 600 billion. It will cross $1 trillion very soon. What is our share? Less than 2%. And that is why this India Semiconductor Mission is launched. Right? We want to be a major player. We can't really miss another bus, right? So that is the vision. And we have to look at all aspects. Again, if you look at this, there are fabs such as TSMC, Global Foundries, Tata Electronics will have fab. There are fabless design houses. NVIDIA, they don't have their own fab. They have IPs. Each one of them will have IPs, right? The IPs in the fab is only in material and process and technology. Whereas NVIDIA, Qualcomm, or even Apple, they have their IPs in design, right? They use the foundries like TSMC, to get the chips made and, and then, put them in the right systems. So today the India Semiconductor Mission has focused on entire ecosystem, on creating fabs, on creating new fabless ecosystem. Fabless ecosystem is already there, but it has to be really scaled up. There are what are called design linked incentives, right? Startups can actually avail these design linked incentives, right? So there's a phenomenal opportunity today. I think we should all come together and leverage this. And interestingly, there's an India Semiconductor Mission and there's also AI mission, right? So recently you probably heard in Long Island, the Prime Minister said, made in India chip will become a reality and this is Modi's guarantee. Right? So if this has to happen, of course, you need to not just have design and also you need to have your own fab and only then you need to build your own technology. Otherwise, you'll get the technology from elsewhere and that's also fine. But 10 years down the line, we should aspire to have our own technology, right? Otherwise, we will not really become a big player. Okay, so I think where we are going in terms of future of devices and chips, as I said, we want to train neural networks on your cell phone. Right? This is the vision, right? It may sound very crazy today, but that's where we will get 10 years, maybe 5 years down the line, right? And maybe you want to charge your mobile phone just once a month, right? That's what we need to aspire for, right? That's where there's a lot of exciting opportunity for not just electronics engineer, but all kinds of engineering disciplines here, right? And data privacy is also important. I mean, you don't want to put all of your data on the cloud. You have to do it now because you have to do every computation on the cloud. But you can bring those compute power onto your edge devices. You don't need to do that, right? Especially health data. There's a lot of privacy involved, right? All of that can be enabled with this future growth of, compute and electronics in the next 5 to 10 years, right? Okay, so let me conclude then. Power dissipation is a stumbling block going forward. We need energy efficient architectures across the board, from materials all the way to systems. One of the options we have to pursue is brain inspired memristor based accelerators. Remember, these are going to be accelerators, right? It's not that you're going to replace the digital completely, right? And we need to reboot the compute hardware, right? The von Neumann architecture has served us for last many decades. In fact, IEEE has a tagline called rebooting computing today, right? So I think we really need to reboot computing and come up with new kinds of hardware and also related software. Because when you build new hardware, you need a whole new software chain also. Right. The point is there's a lot of opportunity, and I think hopefully we can excite our students to come into this area and contribute to this field going forward. Thank you.
Any questions?
Thank you for the wonderful talk. I have two kinds of questions. One is technical, another is operational. So technical side, so you are mixed with the minister going to be taking the total classifier.
We have already done that. I did not cover that. Not just the classifier, we have actually have done complete CNN also. We have implemented, but that the problem right now is that we are still going back and forth, analog to digital, digital to analog. Eventually, we want to do everything in analog. We have not reached that.
So my question was related to that. So whether the path we pursued of going to digital, was it a broad path? It should always have been analog path always.
Well, I won't call it plot path. That was the only path available. As engineers, we take the best path available at a given time. So, yeah. But you see, I don't want to take away all that digital has enabled us, right? Because we wouldn't have been here if it was not for digital technology, right? So even when we do the analog, I think it's not going to replace digital, right? So it will coexist with the digital. Yeah. Correct. Digital is important, but it cannot do everything efficiently. Yeah. Correct. Yeah.
Again, they are moving to analog. So we say that that can just reduce the power or consumption of the information at the core end, so that I can represent that at various levels. So
Right. See, I mean, I think that is very evident, right? Because I gave you an example of how brain is doing everything. Even a big supercomputer will face difficult, like image recognition. I mean, look at how efficiently we can do. I mean, the digital computer will take forever to do that. It is very well known if you can do that, but we don't know how to do that efficiently, because brain also is immune to noise, right? See, when we start implementing these analog building blocks outside, we have to deal with the noise. That's not easy. One beautiful thing with digital is that it gives you huge noise margin. I mean, that is why we have been able to do so many things so efficiently in digital. So now, if we are saying that we want to do analog, now we have to ask the question, how can we do analog despite the noise? That is where we have to come up with the newer ways of doing. Perhaps now that we are not doing a conventional precision computing, remember again, I am saying for the specific analog jobs, not saying that I have two large numbers, I need to multiply. That's a precision computing. I want an exact answer. But when brain does things, it is not just about precision, right? It's reasonably exact, So in that context, some noise can be tolerated. So I think now we have a different paradigm in terms of training the neural network. Even if there is some noise, I'll absorb that noise in my training algorithm, right? But if you tell me use this analog building block and multiply two numbers, give me the exact answer. In presence of noise, I may not be able to do that. So all I'm saying is that depending on the application, one size does not fit all. That's why I'm saying we would still need digital. Digital cannot do everything very efficiently. Those which cannot be done efficiently will do it in analog. Right? They will coexist.
we have 5 sensors. So it's a deductive reasoning such that it takes them to such a realm where you deduct directions and choose the one and code, etc. So that will add to the memory and processing, because we are talking about the memory processor and in between the back and forth information. So there's something happening at the processor level itself, because they are putting the information at that level.
No. See, right now we are not talking about the sensory, inputs. That is a different topic. We were also trying to mimic vision. We are also trying to mimic audio. We have done reasonably well already, right? Your olfaction. We are trying to mimic all of that. That's different. Once you get this perceptory input, eventually it goes here. You see, that is where all the information, storage, computation, inference, decision, all that happens here. See, these sensory organs are working because of this, supercomputer that we have. Today's talk that I had was only about this, not about perception. That perception is also important. I don't know what Professor Susanjit is planning to cover, whether he will talk about sensors. That's also an equally important area. Right? Yeah.
Thank you, Sir. Thank you for me for the great learning. I would like to know how far we have progressed further with the mixtures which you have done in medical application. Have you have any go at it, or still you are working on that, using it in Alzheimer's or Parkinsonism or neural related challenges which we are facing, and even in some cases where the people have disability because of the neural say stroke or anything. How do you think the results here? Or any initial approaches that you made in that area?
Right. So in that context, there are two aspects to it, if I understood your question, because you also made a reference to Neuralink. Right. This is the area of neural processes. Right. Now there are two things. One is you need to be able to, embed things in your body, right? And it should interface with the existing, network that we have. Right there, that perception and sensory thing he was talking about will become important, because you will need what are called electrodes. These electrodes have to excite, the regions of the brain, for example, when you have a, some damaged region. And then what information do you want to use to excite? There you need storage, right? So there are two different aspects to it. The memory stores will enable that storage and computation aspect, whereas eventually you need to be able to probe and you need to be able to measure. There you need sensors, right? There's also a lot of work that is happening in sensors in making a microelectrode array or even a nano electrode array, which is flexible and implantable. So eventually that will have to be integrated along with this memristor element, and then that can be used for this kind of application. Yeah. That is still far, Yeah. Yeah. Correct. Yeah. 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 No, speed of operation, will be very fast. I'll also qualify that. It is fast because of parallelism. Again, this came up in the morning. You have to do things in parallel. See, the reason why, until about end of 90s, we used to give a frequency of CPUs. Oh, it's 10 megahertz, it's 100 megahertz, it's 1 gigahertz. Then we stopped giving that number. Look at anything. They don't talk too much about an individual frequency number. Firstly, it has become difficult to scale that number. That is where this multi-core architecture came. You need to have as many parallel processing units. So they help you in making it fast. The reason why GPU is very fast and also energy efficient is that there are, like 100,000 units working in parallel. And in neural network analogy, there are millions of these building blocks which will work in parallel. Right? So that is why the time will be very fast. In addition to the fact that energy efficiency, that comes from parallelism. Absolutely. That's a very good point because HP Labs invented memristor way back, more than a couple of decades ago. But the problem is the following. The memristor that they invented was based on what is called a metal oxide material. And because of that, the number of states you can store there, you could never exceed 6-bit resolution. Best was 6-bit. That was also with lot of struggle. The excitement today is that this molecular memristor that I showed you has a 14-bit resolution. 14-bit resolution. Right? It is just like in 1947 we invented a semiconductor transistor, which was bipolar junction transistor, right? But we had to wait till 60s, right? Late 60s actually, to start building very complex circuits because transistor was there, but that was not good enough. Only when we made MOS transistor, then things changed. So I wanted to give that analogy. The memristor you talked about was a BJT kind of analogy. And today this memristor can enable something like what a MOS transistor can. There are class of materials which are called molecular materials. It has a transition metal such as ruthenium, which is complex with the organic ligand. Okay, and these materials can be spin coated. Okay, which is compatible with your CMOS technology. No, that's exactly what I was saying. In today's technology, on your edge device, there is no way you can run a very complex model, and there is no way you can train it because the power dissipation. I told you data centers work because there is a huge cooling infrastructure, right? And that is where these kind of devices, which have very high resolution and hence can give you accuracy, at the same time consume very low power, right? They can help. But today we still don't have solutions. Today we still can't do it. But this is a possibility. Right? Yes. No, we still don't have the model files for these. As I said, the model files and all will come, yeah, only when the technology is very mature. This is still evolving, right? There is no way you can simulate and work on this. Right? Huh?
we can proceed neural data later.
You can make an approximate model and do that, but it is not going to be accurate. Correct.
Thank you, sir, for your profound and thought-provoking address and to show us how this technology has elevated from the vacuum tubes to the silicon revolution. And also you highlighted how current AI hardware is very much inefficient, but the human brain is a seat of computation and inference. This address will tell us how do we need to aspire towards the technological growth to cater to the country's progress. This will perfectly aligns with the spirit of today's event. And now it's a time to honor our chief guest. I request the dignitaries to come over to the dais to felicitate our esteemed chief guest. I thank all the dignitaries for the warm gesture of the appreciation to our chief guest. With this, we conclude the inaugural ceremony of the 3-day professional development program on the scaling the future trends and challenges in semiconductor technology. We'll have a tea break for 10 minutes, exactly for 10 minutes. Followed by that will be the next keynote address. Thank you all for joining.